In this presentation, we are going to look at the beta type 2 distribution. So a continuous random variable x is said to have a beta type 2 distribution with parameters alpha and lambda if its PDF is given as follows. F of x equals 1 over the beta function of alpha and lambda times x to the power of alpha minus 1 over 1 plus x to the power of alpha plus lambda. Now you'll notice here we have a range of values that this PDF applies to, and that is 0 to infinity. That's the key difference between this and the type 1 distribution, where the support is 0 to 1. Okay, that has important consequences going forward. In notation, it can be written as x, well, I'll actually rewrite it out, beta 2 alpha and lambda. Now actually, usually I would write actually beta here, but just for some reason beta doesn't work in this setup, so I just had to switch it to lambda. Anyway, so the beta function of alpha and lambda can be expressed as the multiple, or as a sort of combination of the gamma functions of alpha times the gamma function of lambda. Multiply those out and divide by the gamma function of alpha plus lambda. Now typically we could also express that as an integral from 0 to 1 of x to the power of alpha minus 1 times 1 minus x to the power of lambda minus 1 dx. Now this is where the problem sets in with regard to that range of those limits of integration. What we need here is an alternative formulation, okay? And this is the key thing here. Beta of alpha and lambda, which is an integral from 0 to infinity of x to the power of alpha minus 1 times 1 plus x to the power of minus alpha plus lambda. Okay, so I just express as a one-line expression there, but I actually can rewrite that as a fraction. Also, we have the gamma functions, okay, which are always a key part of the gamma and beta function questions down here. So just as a quick remark, the gamma function of n is simply n minus 1 factorial. Okay, you can just disregard those signs there. Likewise, the gamma function of n plus 1 is n factorial, which is n times the gamma function of n. Okay, and gamma function of n is also n minus 1 factorial, which is also n minus 1 times the gamma function of n minus 1. Essentially, there's a couple of little tricks here that follow on from factorials that you can use. Now, this is the key part of this question. What we're asked to do here is calculate the harmonic mean of the beta type 2 distribution. And what we have to show here is show that it is equal to alpha minus 1 divided by lambda. So h, or actually hm as I usually have it, is alpha minus 1 over lambda. So this is the key formula here. What we have to do to calculate the harmonic mean of a random variable is we let 1 over hm equals the expected value of 1 over x. So what we do is we will solve this expression here, the expected value of 1 over x, and then proceed accordingly. Okay, so that is an integral, that's actually of 1 over x by f of x dx. Okay, and from 0 to infinity. So there's 1 over x. This is our expression here. What we can do is take this part out and, put it in front of the integral. We have 1 over x. So essentially what we could do, 1 over x times x to the power of alpha minus 1. So what we can do is re-express that, this here and this here, as x to the power of alpha minus 1 minus 1. Now I'm deliberately sort of leaving it in that sort of vague sort of format, so we can explicitly express it in terms of the two inputs that we're going to try and create for. We're going to try and shape this expression here. We're going to try and shape it as a beta function. Okay, so what we have to do is just make it explicit what the parameters are for this beta function. So the denominator, we have 1 plus x to the power of alpha plus lambda. What we could do is express that as the power of that as alpha minus 1 plus lambda plus 1. Okay, so we have the two parameters there being made very explicit. We have alpha minus 1 up here, minus 1, and then alpha minus 1 plus lambda plus 1. Okay, so that means that that integral can be expressed as follows. The beta function of alpha minus 1 times lambda plus 1. Okay, and what we're going to do is divide that by the beta function of alpha lambda. All right, so that's the expression here. Now, this is where the gamma functions come into play. So it's a lot of cancellations come into play here. Just to remark that this is the numerator, and we express it at the numerator as gamma functions, we get this expression here, and this is the denominator. And when we express that denominator, we get that expression there in terms of gamma functions. Okay, so we just inverted there because we're dividing. Okay, so essentially a lot of stuff is basically going to cancel out. You notice that this gamma function of alpha plus lambda appears in both cases, so they cancel out immediately. Okay, gamma function of lambda can be written as, the gamma function of alpha can be written as alpha minus 1 times the gamma function of alpha minus 1. That's going to cancel out with that. Okay, the gamma function of lambda plus 1 can be written as the gamma function of lambda times lambda. Okay, so this here, and we have a gamma function of lambda down there, so they cancel out as well. Loads of cancelling out, so we're left with lambda divided by alpha minus 1. Okay, now that's 1 over hm. Okay, that's the expected value, so hm is simply, the harmonic mean is simply the inverse of that. Okay, don't forget that step actually. Okay, this is not the answer. This is not the answer. This is the answer. Okay, don't forget that last step. Okay, all right, there we go. Yeah, that's good. The mode of the type 2 distribution, so show that it is alpha minus 1 divided by lambda plus 1. Okay, so this is where we're going to use logarithms. So essentially what we're going to do is take the PDF. Okay, we don't have to worry about gamma functions in this case. What we're going to do is take the PDF and integrate it to find its maximum. Okay, differentiate it to find its maximum. So essentially the key things here are we're going to use the laws of logarithms to sort of simplify things or break expressions up, expressions like that up. Okay, that's the trick really. How do you differentiate an expression like this? It's easier than you think, because what you could do is use logarithms. So re-express or find the logarithm of the PDF, and you know, the same, whatever you do to try and maximize f of x is the maximum. You can find, use the same approach to find the log of f of x. Okay, so to find the value of x that would maximize both essentially. Okay, anyway, so the 1 over the beta of alpha and lambda, so that can be expressed as follows: minus log of beta of alpha and lambda. Okay, remember it's 1 over the beta function, so you know, using log laws, that becomes minus log. The numerator here, x to the power of alpha minus 1. Okay, and when we get the logarithm of that, we use that power law, so we end up with alpha minus 1 times log of x. Okay, and down here, when we get the logarithm of that, it is, again using the power law, minus alpha plus lambda times log of 1 plus x. Okay, now when we differentiate that, that's a constant in terms of x, so that differentiates to 0. When we differentiate that, we get log of x. When we differentiate that log of x, we get 1 over x, so alpha minus 1 over x. And when we differentiate this expression here, we get, particularly the key part there is log of 1 plus x. Alpha plus lambda is a constant, so we can just put that down straight away. So the log of 1 plus x, when we differentiate that, we get 1 over 1 plus x. So alpha plus lambda over 1 plus x. Okay, and that is the expression there. Okay. Now, what we're going to do is let that equal to 0. So when we find the maximum, if we're trying to find the maximum, we let the derivative equal to 0 and solve for x. So what we're going to do there is, solve that for x. Let that solve for x. So alpha minus 1 over x minus alpha plus lambda over 1 plus x equals 0. What we can do there is just bring them to both sides of the equation. So alpha minus 1 over x equals alpha plus lambda over 1 plus x. Cross multiply. Okay, so when we cross multiply, we get alpha minus 1 times 1 plus x, which can be written as alpha minus 1 plus x times alpha minus 1. Okay, and of course the other side, x and alpha plus lambda. There we go. Simplifying it out, we get this expression here. Essentially, we want the whole thing in terms of x, and so we should end up with alpha minus 1 divided by lambda plus 1 when we just sort of work through that expression, just essentially simplify it out. Now, that should be okay. Now, essentially what we have to do is apply the second derivative test. Okay, now, the second derivative test is that we get the second derivative and see if it is negative or 0. Now, that works slightly differently when you're dealing with probability distributions, because probability distributions are, by definition, always positive. So if you're trying to find the maximum, you just really, they always have a sort of shape like this, or like this. Okay, so you're never really interested in the minimum. It's always a maximum. So the rules are slightly changed when you're dealing with probability distributions for the second derivative test. Basically, you have to just show that it's 0. Okay, that's all. And you can almost state it usually, because what happens is that there's no expression of x there in this. There's no x component here. Okay, when we get the second derivative of that, so when we let it equal to 0, so just, let it solve itself. Okay, and we should let it equal to 0, and that means our mode is alpha minus 1 times lambda plus 1.